Welcome back for the mechanical vibrations video lectures. In this video lectures, we are deriving the equation for free damped vibrations. So the equation we are going to be called, that is the equation of motion or the characteristics equations of the free damped vibrations. So in the previous video lectures, we have discussed about the free damped vibrations, right, and the different types of the damping systems we have seen, right. So here is going to be the differential equations of motion, the damped free vibrations. As you know, here is the damped means here that is going to be the resistance force is offered by a medium. So in this case, what will happen? In the last few video lectures we have seen that the spring and mass system, but in this case one external devices we added, that is going to be the cylinder as well as the piston. That means here that is going to be damped. So that means the piston is moving in the fluid so that the fluid friction is going to be generated. That is called the viscosity. Right, the viscosity is nothing but the wet friction we are going to be saying. So then what happened when the system is going to be starting vibrating up and downward directions, then the piston and cylinder started to move in one direction, that means in a different direction. That means here the velocity of this object is going to be, the fluid is going to be displacing into the other directions of that cylinder, so that the energy is going to be losing is going to be taking place. So for this one, we can see here the K is going to be the spring constants, and C is going to be your damping coefficients, and M is going to be the mass of the system, and next we are going to have the Fs is going to be the spring force, that is going to be K into deflection. So next, the force due to damping, that is equal to the coefficient of deflection, the damping coefficient and velocity. Next one, the inertial force that we know, mass into acceleration. So once we are familiar with these terminologies, now we have to draw the free body diagram. We assume that we given the initial displacement to this system, it is moving in the downward direction. So once it is moving in the downward direction, the accelerating force is going to be acting in the downward direction, but the inertial force is acting in the opposite direction. So I am going to be taking here the free body diagram for this part. So that's going to be, I am taking the mass of that system, that is going to be the M. Then we know that when this is moving, the spring is and the damper is elongating in the downward direction, but the restoring force of the system is going to be acting in the upward direction. That I am going to be saying here is going to be Fs is going to be the spring force which is acting in the opposite direction, because that is the internal forces are developing because of that force. Next, it is going to be the Fd is going to be called the damping force. And next one, this is going to be called the Fi. Fi is going to be the inertial force. As you know, the algebraic sum of the dynamic forces are acting on the system is equal to 0. So that is going to be sigma F is equal to 0 I have taken. So what is the sigma F here? How many forces are acting? 3 forces are acting. That's going to be inertial force plus damping force plus spring force, that's equal to 0, because we are given only the initial displacement. After that we remove the force, that's why we have taken here 0. But if the force is acting continuously, then this is not going to be 0. That acting force we have to take it here. Then what is Mi here? Fi is here, that's going to be mass into acceleration plus Fd is equal to formula, that's going to be coefficient of damping and velocity we have taken, plus F is equal to A into X is equal to 0. These we are going to be called equation of motion. From here we will derive what is the natural frequency of the system and what other parameters also we are going to be considering. So in this case we can see there is a X parameter is there. X is going to be the displacement, right? And how it is going to be displacing. But when it comes to the simple harmonic motion, that's we written X is equal to A sine omega t, because that motion of this vibrating system is following the simple harmonic motion. But in this case, it is not following the simple harmonic motion because we added the damper. That means energy or the vibrations of the system is going to be dying out in an exponential manner. That means the system is going to become within equilibrium positions within the no time. So that's why here the energy dissipation is taking in terms of exponentially dying out. So then what happened here, that I am going to be taking, I am assuming that how the energy or the displacement is going to be taking place. That the displacement that is going to be X is equal to, what is the formula we do have? A e to the power of lambda t I have taken here. In this case, as you know that X is going to be the displacement of the or amplitudes of the vibrations, and A is going to be, we are going to be called the maximum amplitudes of that vibrations, and e to the power of means this is going to be the energy is going to be dissipating. So that is going to be exponential rate. So that is the lambda is going to be the constant one and the theta is going to be the time interval. So then in this case the lambda is going to be, we need to calculate from this equation. So then what is the formula we do have? Suppose if you want to substitute in this equation, we need to derive with respect to the time. So then what happened? I am going to be deriving, that means dx by dt that I have mentioned here, that is going to be x dot. So that's going to be the velocity. That's a into lambda into e to the power of lambda. And once again I am going to be deriving the velocity. That's we are getting here. Acceleration. That's going to be a into lambda square e to the power of lambda. So then these three, displacement, velocity and acceleration, I am substituting in this equation of motion. So then what is the equations we are going to be getting? So that's going to be m into a lambda square e to the power of lambda t plus c a into lambda e to the power of lambda t plus k into a e to the power of lambda t, that's equal to 0. Alright? So we got it, that is equal to 0. In this case, some common terminologies we do have, that is the maximum displacement of that vibrating system A is going to be, we are going to be making the cancel out. And e to the power of lambda t also is the common. So that I am going to be taking to the one side. So that's going to be m lambda square plus c lambda plus k is equal to 0. And thus we got it in a quadratic equation. So now we need to calculate the lambda. As we know that this is going to be ax square plus bx plus c type equation. So then we are going to be calculating by equation of that. That's x is equal to minus of b plus or minus square root of b square minus 4ac by 2a equation we are using. The same equations I am going to be taking here. The lambda 1 comma 2 is equal to, what is the formula we do have? So in this case I am going to be simplifying this equation before this one. So simplification is going to be lambda square plus c by m lambda plus k by m is equal to 0. By using this one, I am going to be deriving the equation of that one. That is going to be lambda 1 comma 2, that is equal to, what is the b here? That's we are saying minus b means minus c by m plus or minus square root of c by m whole square minus 4ac. So what is the 4? A is going to be m. So sorry, that is going to be 1 here coefficient and here is going to be the k by m. 4k by m we do have, that's divided by 2a. A is going to be coefficient is going to be the 1 here. So after this solving this equation, then the 2 I am going to be taking to the numerator. So then what formula I am going to be getting? Lambda 1 comma 2 is equal to minus c by 2m plus or minus the square root of c by 2m whole square minus k by m we will get it. So this is going to be the equations we got it. So that I am going to say. This is going to be the lambda 1 and 2. So from here we calculated the lambda 1 and 2. Just I simplified that one, the lambda 1 and the lambda 2. The lambda 1 is equal to minus c by 2m plus square root of c by 2m whole square minus k by m. In this case, lambda 2 is equal to minus c by 2m minus the square root of c by 2m whole square minus km. Then we do have that equation, that's going to be x is equal to a e to the power of lambda t. In this case, we do have these roots are going to be, the two roots are available, lambda 1 as well as the lambda 2 for the two faces. That's going to be, I have modified this equation into x is equal to a1 e to the power of lambda 1t plus a2 e to the power of lambda 2t. So then I substituted lambda 1 and the lambda 2 in this equation. So then that is going to be, this equation we are getting x is equal to, this is the equations we have derived. So from these equations we are going to be calculating the, what is the critical damping, what is the over damping and what is the under damping. All these equations we are getting from this equation. This is the displacement of the system. This means the displacement each and every cycle, we know that it is going to be dissipating the displacement each and every time. So that's going to be exponentially, it is going to be decrement is going to be there. That on that assumptions we have calculated the displacement of the system from the equilibrium position.